All right. For today's lecture, we're going to begin talking about covalent bonding. And the first module here, we'll talk about what we call molecular orbitals. So to begin with, let's again review really quickly what covalent bonding is. Right? Covalent bonding is that opposite version of ionic, where instead of a transfer of electrons, we have electron sharing. And so um, that those electrons that are shared tend to spend more time between the nuclei of the two atoms, right? So if here we have lithium and hydrogen, and so the electrons will spend more time between the nuclei as opposed to outside of the nuclei. So that's the case with all these various molecules that we see here. So we're going to look at covalent bonding in terms of molecular orbitals, sometimes shortened to MO, because the way we think of these molecular orbitals is basically combinations of atomic orbitals. And so with orbitals, we're talking about electrons, right? And so, for example, we looked at, for example, the 1s orbital, which is spherical in nature. So the electron cloud is spherical. And so basically what we want to look at is, well, what if two atoms with 1s orbitals bonded together? And so we think of that as a molecular orbital by kind of summing the two density maps that we have here into this bonding molecular orbital, where the electrons spend most of their time between the nuclei because there's a bond between them, right? So this is bonding molecular orbital for these two 1s atoms. However, there could also be what's known as anti-bonding molecular orbital. And this is the case if the signs are different. So again, the sign here is not charge, it's the sign of the wave equation. So this is a positive, and then this is the negative. So if this happens, when we summarize these two atomic orbitals into a molecular orbital, we get what's known as delocalization, because we have essentially a node over a lobe over here with positive charge, and then they cancel out in the middle, and you have a negative sign here, positive over here, and then in the middle, because they've canceled out, so that middle portion is canceled. You get what's known as a nodal plane. So it's basically a vacuum of electrons. So this is known as the antibonding molecular orbital, because here the electrons, instead of spending their time in the middle between the two nuclei, they are either on one side or the other. So this is a kind of unstable version of what's happening here. So this is a very strong portion, and then this is delocalization. So we can think of these in terms of energy. And so, we're looking at the same scenario here. So this is energy, just relative energy. One atomic orbital isolated is situated here, and then another atomic orbital, so the example of the 1s and the 1s, so they're at the same energy level. If these two come together to form a molecular orbital, the bonding molecular orbital, which forms the bond and the electrons are between the nuclei, lowers the energy, so lower on this relative energy scale. And then the antibonding molecular orbital raises the energy up. And if you're wondering, why we have this, well, if you think about these orbitals, right, an atomic orbital, if this is the 1s, it can hold two electrons. This can hold two electrons, and so when we get a molecular orbital, we have to maintain those sites, right? So 2 plus 2, we have to have 4 sites. So there's effectively a position for two bonding molecular orbitals, and then same thing for the anti-bonding. So that's what we'd have, and this is just a profile showing the same thing that these are showing, but just in a kind of a two-dimensional order. All right. So again, the overlap of those positive sign wave functions, Schrodinger wave function, creates the bonding molecular orbital, and then the negative sign creates the basically subtract and form that nodal plane. And so that's what you can see with that. All right. So when we start looking at these molecular orbitals, again, we often want to think about the symmetry. And so here we're referring to symmetry about the line of the two nuclei. So effectively, if you look at all these, kind of ignore the shapes and stuff for now, but just this line across that's Z, basically the Z-axis here, that's the line running through the two nuclei. And so what's happening here is we're forming together two orbitals. So you see here, this is an atomic orbital, here's another atomic orbital. And basically what we're looking at is these two form together, the pluses are next to each other. And so if they are next to each other, basically they'll add together and you'll get a shape like this, where you have a positive lobe and then negative lobes on either side, and then nodal planes in the middle with the dashed lines. Same thing here, if the signs are reversed, you'll actually get a positive, negative, and then actually these become larger relative to those. And so these are sigma orbitals. So these are the strongest bonds because they have overlapping. You can see that they're overlapping in these lobes that we get. So that's the sigma. So let's look at another type. So if the orientation is parallel now, like this, then what happens is the positives kind of combined, the negatives combined. We have a nodal plane here. Same thing here, but we have the positive and a negative, positive and a negative. These are known as pi bonds, or sorry, pi orbitals. They are, again, from the p-type. All of these are p-type, but these are weaker, and it's really to do with the symmetry here. So these pi orbitals are not symmetric about the line, the line of axis of Z here. So if we look at Z, if you take a spot over here, it's negative, and then if you cross the nucleus, we also have positive here, and so the symmetry is different. And the same thing over here, minus positive. But if you look over here, we have the same charge on either side of that axis. So we have that type of symmetry. So basically, pi orbitals are not symmetric about that line, but sigma are. And that has to do some with the strength of these bonds. A sigma being strong from that overlap, and then pi being weaker bonds. And so let's look at the relative energies when we go from, again, atomic to molecular. So if we're looking at 2s and 2p, this is the energy axis going vertically. So s is going to be lower than p. And then when the 2s bonds with another 2s, we get a sigma bond. So this is the bonding and anti-bonding. And then with the 2p, remember we have three orbitals in each of those. And when those merge together, we have sigma bonds that you see, bonding and anti-bonding, but we also have two pi bonds, which again are weaker. So we have bonding and anti-bonding for those two sigmas. They're just at the same energy level, so that's why we have the overlap. All right, so these are kind of these relative energy diagrams that we can do for atomic or molecular orbitals. So what I want you to do now is, in the quiz, you'll have the same question, but see if you can sketch a specific molecule, thinking about hydrogen fluoride or hydrofluoric acid, if you want to look at it. So HF. So consider the HF molecule, so hydrogen and fluorine, atoms coming together. Think of it as this molecular orbital, and see if you can draw both the atomic orbitals for H and F, and then compare that to the molecular orbital of the HF molecule. So see what you get. Again, if you don't get everything perfect, that's fine, but do that, pause the video, and come back, and we will take a look. All right, so let's look at this HF molecule, but first, let's look at hydrogen by itself and fluorine by itself. So with hydrogen, we have 1s1, right? One electron, the atomic number is 1, so we have 1 proton, 1 electron. And so when we draw that, again, keep in mind this, we're just very crude kind of energy axis here, if it focuses. All right, so we've got this is kind of this is the 1s orbital, and so since we only have 1 electron, I'll put that as the spin up, right? And then we have a vacancy, right? So there's one more spot for that. So that's what we have for hydrogen. Really simple because we only have 1 electron. Fluorine, on the other case, has a lot more electrons, and so we're just going to focus on the 2s, 2pf, because these are the outer valence. The others are the 1s is basically full and at a much lower energy, but these are the valence electrons, and so we know that the 2s is lower than the 2p, and it's full, right? So we have 2 electrons, and then there is 1, 2, 3 p orbitals, right? Because of the L number, and so there's 5. So we're going to fill for this one. We're going to fill so obviously I'm not assigning X, Y, and Z to this. So basically, just keep in mind that I have 1 vacancy here of these 2p orbitals. So this is 2p, this is 2s, and this is the 1s. So so again, since this is unfilled, it's at a higher energy state than the 1s for fluorine. But again, I'm not expecting you to know the exact energy levels here. We're just kind of using this as a crude model. So when these blend together and form a molecular orbital, we're going to look at HF, right? So that's kind of the interest that we want to look at. So if we look at this, only one of these is partially filled, right? This one, and then this is partially filled. These are already filled, so we probably won't deal with those, right? So for this, we are going to kind of make the bonding and anti-bonding molecular orbital. So the bonding, again, we have we're merging this and this, right? So we have 4 spots. I drew that badly. I should have just drawn one large spot because we're only trying to fill 2. So in this case, we have 2 electrons, and these 2 orbitals combined, we have to have 4 sites, right? So 1, 2, 3, 4. So, but we only have 2, so we can lower the energy by putting both of those electrons in this spot right here, and this is the higher energy state is unfilled. So the bonding molecular orbital is filled, the anti isn't. And then the other 2, these 2p, and the other 2p basically remain in the same spot. So these are basically just at the same energy level, but these are lowered, so the one from this and the run from over here. And that's what we get. And this doesn't change either. We have the 2s here. But we do get a bonding molecular orbital and the anti-bonding molecular orbital. and then these are two P's. So that's roughly what we would look at for this type. So let me switch over to the slides, and I'll show you this in a little bit more detail with a spatial model of HF. All right, so again, we're looking at HF. This is what I basically drew for you. It might look slightly different, but take that with a grain of salt. But what I drew for you on the piece of paper is basically what you see here. But the one thing I wanted to kind of point your attention to is since this is HF and we're dealing with the 2p from fluorine, the 2p's, if you remember, the orbitals look like this, right? So they're along the x, y, and z axis. And then we have hydrogen, which is a simple 1s, so it's spherical. So you can think of the hydrogen atom along one of those directions, right? So it's bonding with one of them, in this case the y, which is why they've done the middle one that we worked with. And so, but the others are unaffected. So that's why the z and the y are basically remain unaffected in that case. And so we have bonding between the 2p x and the 1s from hydrogen. And so that's kind of just a spatial representation of what I showed you here with the energy diagram for hydrogen fluoride.